Today, we're gonna be looking at something pretty wild.
Oh, yeah.
Yeah. So get this. Like, what if we could build neural networks that like come preloaded with knowledge?
Yeah.
Like a brain with an instruction manual built in.
Okay, that's a pretty interesting thought. You're talking about kind of like combining the flexibility that you get with neural networks
Yeah.
with the precision of an algorithm.
Yeah, like having your cake and eating it too, right?
Exactly. Best of both worlds.
So that's what we're diving into today. We've got some sources here on the work of this Dr. Hava Siegelman.
Okay.
And she's done some really cool work on how to actually like translate computer programs into the structure of a neural network.
So instead of starting with like a blank slate, it's like you're giving these networks a head start.
Yeah, exactly. Like imagine trying to teach someone how to play chess.
Okay, yeah.
You could just like let them play randomly and figure it out themselves. Or you could be like, hey, here are the basic rules.
Right. Give them a foundation.
Yeah, and that seems like a much better way to learn.
It makes sense. And actually that kind of highlights one of the limitations with like traditional neural networks.
Oh, how so?
They're really good at things like pattern recognition, image recognition even.
Yeah.
But when you need explicit knowledge or rules, that's where they struggle a little bit.
And you know what? Our sources actually give a great example of that. Functional electrical simulators.
Okay.
So using these things with patients that have spinal cord injuries to try to, stimulate movement, generate the right kind of stimulation.
No.
And it turns out that traditional algorithms have a really tough time with that.
Really?
It's just too complex.
Okay.
But machine learning is showing a lot of promise there.
That makes sense, yeah.
Yeah.
Machine learning is all about finding those patterns in complex data, so it seems like a good fit.
Totally. Okay, so how does this translating programs into neural networks thing actually work? Like, what's the magic behind that?
Well, it's not magic, but it's pretty darn close. So Dr. Siegelman developed this thing called neural language, NEL for short.
Right.
It's a programming language that basically creates a bridge between those traditional algorithms and our neural networks. So you can write a program in NEL, and then it gets directly compiled into the structure of a neural network.
So you're basically building a network of neurons that represents the program's logic.
Exactly.
Okay, that's pretty wild.
Yeah.
But how can a neural network understand something like an if-then-else statement? I mean, isn't that like programming 101?
Oh, yeah. It's super fundamental. And the source actually has a cool example that kind of illustrates this.
Okay.
So think of a neural network. It's got just a few neurons.
Okay.
And depending on whether a condition is true or false.
Like if a number is bigger than 5 or something like that.
Exactly.
Wow.
Yeah. The neurons will activate in a specific pattern.
Huh?
And that pattern represents the outcome of that if-then-else statement.
So the network is actually making a decision
Yep.
based on the information it's getting.
Exactly. And it's all guided by those rules that we pre-programmed into its structure.
Okay, so my mind is officially blown. But hold on a second. How do you actually represent different types of data within a neural network? Like, you can't just store a list of numbers or texts directly in a neuron, can you?
No, you can't just shove it in there. It's a good question. And it kind of gets to the heart of how NEL actually handles complexity.
Okay.
So it uses these gaps, I guess you would call them.
Gaps.
Yeah, in the range of possible neuron activation values to represent different elements of that data.
So give me an example, because I'm not following it.
Sure. Imagine you want to represent like a list of ones and zeros in the neural network.
Okay.
Instead of directly encoding those digits, you could use specific gaps in the numbers between 0 and 1 to represent each element of that list.
So like, instead of a neuron's activation value being, say, 0.6, it might be like 0.62 to represent a 1,
Yeah.
and 0.65 to represent a 0,
Okay.
something like that.
You got it. And this whole encoding scheme allows you to do cool things.
Like what?
Like adding an element to the list, reading the first element, removing elements, all within that neural network framework.
So it's not just like mimicking the logic of the program, it's actually like manipulating data
Right.
in a way that mirrors those instructions.
Precisely. And this method, it's not just limited to lists. You can use it for other data types too, like stacks, counters.
Wow, so it's pretty versatile.
It really is.
Man, this is getting deep, pun intended.
Well, speaking of deep, one of our sources mentioned this universal network concept. Have you heard about this?
I don't think so. What's that?
So apparently a network with just 886 neurons and simple rational weights can actually compute any computable function.
Wait, really? any computable function.
It's crazy, right? And that finding has some pretty big implications.
Yeah, I bet. Like if a relatively small network can do that, imagine what you could do with larger, more complex networks.
Exactly. It makes you wonder what the limits of these things really are.
It's like we're just scratching the surface.
And it gets even wilder. The source also talks about how neural networks using real numbers, which have infinite precision, could potentially do computations that are impossible for digital computers.
Hold on, back up for a second. What does it even mean for a network to use real numbers?
Right, that was a bit of a jump.
Yeah.
Okay, so to get this, we got to talk about analog versus digital. Think of a dimmer switch.
Okay.
You can gradually increase or decrease the brightness, right?
Yeah.
That's analog continuous values. A regular light switch, it's either on or off, that's digital.
Okay, so how does that apply to neural networks?
Well, most computers and most neural networks are digital,
Right.
working with those discrete values, zeros and ones.
Right.
But if you could build a network that uses analog components where the neurons can have any value within a continuous range.
It seems like that would open up a whole new world.
Exactly, and that's what Dr. Siegelman's work is pointing to.
So these analog neural networks could be way more powerful than what we're doing now with digital systems.
Potentially, yeah.
Wow. Okay, my brain is like officially fried right now. We've got this crazy new programming language that can translate algorithms into neural networks,
Yeah.
give them a head start. And on top of that, we've got this whole other level of analog networks that could just, I don't know, break the rules of what we thought was possible.
Yeah, it's pretty mind-blowing stuff.
It really is. This is just the beginning though, right? Like there's so much more to learn about this, the applications, the implications.
Oh yeah, for sure. We're
Look-
just getting started. There's a whole universe of possibilities out there.
Man, I can't wait to dive deeper.
So we've talked a lot about like the nuts and bolts of how this all works.
Yeah.
But I'm kind of curious about like the real world applications of this. Like where could this technology actually make a difference?
Yeah, that's a good point. Like, it's cool that a network can understand an if-then-else statement,
Right.
but what does that actually mean for solving real problems,
Yeah.
you know?
Yeah, exactly. Well, one area where this could be huge is robotics. Imagine being able to program robots with like safety protocols built in.
Oh.
So that no matter what, they operate within certain ethical boundaries, you know?
So, like, preventing those sci-fi movie scenarios where robots go rogue and stuff.
Exactly, yeah. Like, what if you could hardwire those rules into their very structure?
That's pretty wild. And I guess it goes beyond just safety, right?
Oh, yeah, for sure. Think about like robots working in healthcare.
Oh, yeah, that's a good one.
You could program them with an understanding of medical ethics, patient privacy, things like that.
So they're not just blindly following instructions.
Right.
They actually have some kind of, like, moral compass built in.
Exactly, yeah. Like a foundational understanding of right and wrong just baked right into their neural networks.
Okay, that's pretty powerful. What about other fields? Like, could this be applied to finance or transportation?
Oh, absolutely. I mean, imagine financial algorithms that can learn from market trends, but are also, bound by regulations
Right.
to minimize risks. Or self-driving cars that are programmed with like a deep understanding of traffic laws.
So it's like taking the best of both worlds, the learning and the rules.
Exactly. And that's where it gets really interesting.
Yeah, it does seem like the possibilities are kind of endless.
Ah.
But,
Yeah.
I do have one concern.
Oh, yeah. What's that?
If we're talking about embedding, like, ethics and rules into AI, who gets to decide what those are?
That's the million-dollar question right there. And it's something that, researchers and policymakers are really wrestling with.
Yeah.
We need to have some serious conversations about the values, the principles that we want to bake into these systems.
Yeah, we don't want to just, like, replicate existing biases
Exactly.
or create a system that only reflects, a narrow set of values.
It's a tough one, but it's something we can't ignore.
Okay, so let's shift gears a bit. We've been talking a lot about NEL and how it bridges this gap between algorithms and neural networks.
Yeah.
But you mentioned earlier that NEL isn't meant to, like, replace traditional machine learning, right?
Right. It's not about replacement. It's more about adding another tool to the toolbox,
Good.
Machine learning is still super powerful for certain tasks,
Yeah.
especially things like, finding patterns in massive data sets.
So it's not about throwing the baby out with the bathwater.
Exactly.
It's about having more options.
Right. And in some cases, It might even be about combining the two approaches.
Oh, interesting.
Like, imagine a system that uses NEL to establish a foundation, like you said, of rules or principles.
Okay.
And then it uses machine learning to kind of adapt and refine that knowledge based on real-world experience.
Oh, so like a hybrid approach.
Exactly. Using the best of both worlds. It's exciting stuff.
It really is. I mean, this whole deep dive has been pretty incredible. We've gone from
Yeah.
like the nitty-gritty of how this NEL thing works to, the mind-blowing potential of analog computation.
Yeah, and we're talking about the ethics of it all.
Right. It's a lot to take in.
It is. But we're just scratching the surface, There's so much more to explore.
You know what's funny? We started this deep dive talking about bridging the gap between algorithms and neural networks.
Yeah.
But it feels like we've stumbled onto something much bigger. Like a whole new way of thinking about computation, about intelligence itself.
I totally agree. It's like this research is blurring the lines between the rigid structure of algorithms and that adaptable nature of neural networks.
Right.
Like maybe there's this deeper level where these two approaches kind of converge.
Yeah, where the line between programmed and learned behavior gets all fuzzy.
Exactly. It's like we're seeing the birth of this hybrid intelligence.
And who knows what it'll be capable of, what problems it could solve.
It's exciting to think about. That's what keeps researchers like Dr. Siegelman going, pushing those boundaries.
Well, my brain is definitely buzzing with possibilities after all this.
Mine too.
All this talk about analog neural networks and the future of AI.
Yeah.
It's a lot to process, but it's really fascinating.
It is.
I'm ready to dive into some more details about how these analog networks actually work, though.
Okay.
Like, what are the mechanisms? What are the challenges in building them?
Yeah, let's get into that. There's definitely a lot of research and development happening in that area.
So we keep talking about these analog neural networks being able to outperform digital computers.
Yeah, it's a wild idea, right?
Yeah, like tapping into this whole other realm of computation that we don't even really understand.
It really makes you wonder, what's the true potential of neural networks? Maybe it's way bigger than we ever thought.
It's kind of mind-boggling.
Yeah.
But okay, so how would you actually build one of these things? What would the physical parts of an analog neural network even look like?
That's where it gets really interesting, and that's where a lot of the current research is focused.
Okay.
And one really promising avenue is using these things called memristors.
Memristors. I feel like I've heard that word before. They're like resistors with memory or something.
You got it, yeah. They can basically remember how much charge has flowed through them.
Okay.
And that makes them perfect for simulating the behavior of synapses in a neural network.
So instead of using transistors like in a regular digital computer, you could use these memristors to create a network of analog neurons that can change their connection strengths.
Right.
Based on how much charge is flowing.
Exactly. And because memristors can hold this continuous range of values, they give you that infinite precision that we were talking about before.
Which could lead to those super digital computations.
Exactly.
Okay, that's starting to make sense. But it still sounds like there are a ton of challenges.
Oh yeah, for sure. It's still super early days.
Like what kind of challenges?
Well, we need to figure out how to manufacture memristors reliably on a large scale.
Yeah, that makes sense.
How to actually design these networks.
Right.
How to program them effectively. It's a whole new ballgame.
It's like a whole new field of engineering just waiting to be explored.
Totally. And it's not just the hardware. We also need to come up with new algorithms, new programming languages that are specifically designed for this kind of analog computation.
Yeah, NEL's a good start.
It is.
But it sounds like we're just at the very beginning.
Oh yeah, absolutely. We're just scratching the surface.
This is all so exciting, but I gotta admit, I'm also kind of intimidated by all of this.
Yeah, I get that.
It feels like we're on the verge of a technological revolution.
It's a lot to wrap your head around, that's for sure. But I think it's also super inspiring, We're seeing a whole new era of computing being born, and it's going to change everything.
I think you're right. It's exhilarating and a bit daunting all at the same time.
It's a wild ride, that's for sure, but it's a ride worth taking.
I totally agree. So for our listeners out there, I guess the takeaway is don't be afraid of the unknown.
Yeah. Keep asking questions, keep learning.
Who knows what you might discover?
Exactly. We've only just dipped our toes into this incredible field. There's so much more out there to understand.
And it's not just about the technology itself, right?
No, it's about us, too.
As we learn more about these neural networks,
we're learning about intelligence itself.
About what it means to be human.
That's a good way to put it.
This has been an amazing deep dive.
It really has.
And I'm so curious to see where it all leads. Thanks for joining us on the deep dive.
It's been a pleasure. Until next time, keep exploring.